Meet Bob, a physics student who is going bowling with his friends. Bob's friend finds two bowling balls, one of which is 1 pound and the other 10 pounds. He asks Bob which would fall faster. When Bob's teacher asked him this question, he was quick to say that they would fall at the same speed due to having the same gravitational acceleration. However, when faced with the same problem in real life, Bob claims that the 10-pound ball would fall faster because it weighs more. Why would Bob, who knows the right answer in class, give the wrong answer when faced with a real-life scenario? Today we're looking at resource theory and how it helps us think about transfer of knowledge, specifically in physics education research. For a very long time, unitary ontology dominated in the education research field. It's the idea that knowledge is a stable thing that you either have or don't have. Unitary ontology views misconceptions as hard, intact elements that need to be replaced. Eventually, constructivist learning theory came along to shift the focus, showing that new knowledge is continually built on top of what came before it. The point of it is not to replace old ideas, but to refine them. This is where resource theory and knowledge in pieces come into play. Both of these learning theories suggest that people's ideas about the world originate from small, intuitive building blocks, which are called phenomenological primitives, otherwise known as p-prims. What is the difference between resource theory and knowledge in pieces? Knowledge in pieces works better with fine-grained, detailed models, whereas resource theory takes a more broad approach, focusing on simpler, flexible elements that can explain thinking across contexts. Resources can be thought of as small, reusable pieces of thought, such as the idea that closer is stronger. What is transfer? Within this framework, transfer is not about moving fixed knowledge from one situation to another. Rather, it's about whether relevant resources get activated in a new context. Sometimes it's just passive. Just seeing the idea again in a new setting can spark recognition. Other times, it's deliberate. The learner has to consciously apply what they know. This explains why transfer improves for students who see an idea in multiple contexts, multiple subjects, or in real life versus in class, or with metacognitive support to help them notice the connection, such as teachers who help make them aware of what they're thinking about along the way. How does transfer happen? In resource theory, every act of thinking, including recall, involves activating different sets of resources. Therefore, transfer is not about carrying knowledge, but about reassembling it in context. A student might activate one set of resources when solving a textbook problem, such as resources learned from studying, and a different set when casually talking about the same physics principle, activating observations from experiences. So when Bob says heavier falls faster in his real-life situation, but correctly answers that neither falls faster in the classroom, this is not a failure. Rather, this is a glimpse into how knowledge is fluid and built from resources that activate differently and shift within different contexts. Educators need to help students recognize, refine, and reactivate their ideas so that they can build deeper, transferable understandings of topics.